Hello everybody, thank you for joining us. We're very excited to bring you today's webinar from Saft, where we will be talking about how to keep your energy storage system flexible in times of changing market conditions. So the lithium-ion battery has changed all of our lives, and last year its inventors were awarded the Nobel Prize for Chemistry for what was described by the prize committee as their part in creating a rechargeable world. Now, if you're watching this webinar, you're probably already somewhat aware of the growing role battery storage is playing in modernizing and decarbonizing the grid. And of course, it's not as simple as just storing energy for when the sun doesn't shine and for when the wind doesn't blow. It's about delivering a range of different services, and you need to have systems you can trust to be capable of doing that. I'm Andy Colthorpe. I'm the editor at Energy Storage News. I've been covering this industry for about 6 years now, and I'm your presenter for today. I'll also be helping to moderate the Q&A at the end of the presentations. You can enter your questions for our speakers in the panel that you can see on the right-hand side of your screen for that Q&A. And don't forget to take part in the poll too, which we're just about to bring up for you. You can also respond to that poll in the tab on the right-hand side of your screen, marked polls, of course. And of course, the poll is, as you can see in front of you, what are the main challenges in doing business with energy storage systems today? Are they technical, business, financial challenges, environmental, or regulatory challenges? And yeah, we'll be taking a brief look at that when we return after the presentations. Now, as a journalist, I'm sorry to say that I probably spend more time looking at Twitter and LinkedIn than anyone would want to. But I did want to share with you a couple of interesting tips that I've come across recently. And one of them comes from Dr. Kai Philip Caries, who is an energy storage expert at RWTH Aachen University. And it's about how to improve the longevity of your cell phone battery. And he writes, never charge overnight. Instead, use the time during your morning routine for juicing up your phone. By minimizing the time spent fully charged, the battery will retain its usable capacity for years to come. And the other tip comes from Dr. Ewan McTurk. He's an EV expert, an electrochemist, and he's the owner of the Plug Life YouTube channel. Now, this advice from Ewan was given during the coronavirus lockdown, but I think it's still handy to know. And if your electric car is sitting idle for a long time, don't leave the battery fully charged, as the electrolyte will degrade against the cathode, the positive terminal, when the cell is still at high voltage. Leaving it between 50% to 80% state of charge prevents the battery from being at too high voltage and from degrading, while being at least 50% will prevent the battery from being over discharged after being left too long at a state of low charge. So that's EVs and cell phones. So you can imagine that when we look at energy storage at multi-megawatt scale, getting maximum value out of batteries for as long as possible safely, that's when things start to get really interesting. Now, we're hearing from those in the market that battery storage systems can and should perform multiple tasks, from fast responding grid services, applications that require high power and short bursts, to arbitrage and trading increasingly. And those are applications that require longer durations of energy as opposed to power. Today, we're going to be talking about creating and deploying the right size systems to be operated safely and within clearly defined parameters, creating the maximum benefit economically and environmentally. Now, I'm going to leave it up to the experts from Saft to talk you through some of those options in a lot more detail. But in short, what today and tomorrow's markets require are flexible assets that enable intelligent balancing of the grid. So, leading the presentation will be Michael Lippert. He is Director for Innovations and Solutions for Energy at Saft. Michael is also the Vice President of the European Association for Storage of Energy, EASE. He's also Chairman of the Board at Batteries Europe. Joining us will be Michael's Saft colleagues, Jan Laut, who is Director of Services and Solutions, and Jim McDowell, who is Senior Technical Advisor. We also have a special guest appearance from Daniel Lecombe at Total Solar. And Daniel is Total's Vice President for Energy Storage, and he'll be bringing us an end customer perspective. So without further ado, we will go over to you, Michael.
So thank you, Andrew, for this introduction. Hello, everybody, and thanks very much for joining us today for our first webinar on energy storage systems. My name is Michael Lippert, and I'm very happy to talk to you today about flexible energy storage seen from the perspective of a developer, manufacturer, and integrator of lithium-ion battery with Saft. So what have we prepared for you? First, why do we need flexible energy storage? We will look at this question from a general point of view first, followed by a real-world example with a real customer. We will then share our 3 main ideas on how to remain flexible and talk about the benefits we see for developers and operators. My colleague Jim and Jan will dig more into the technical details of these recommendations afterwards. And finally, we will show you some design options we have deployed around a real case 25 megawatt system. So let's start right away. Why do we need flexible ESS? Well, those of you who are operating in Europe may know this screenshot. It's the auction platform for ancillary services called Regelleistung for German, French, Belgium, and other European TSOs. FCR, which means frequency containment reserve, or otherwise called primary frequency response, is dealt on a daily basis, whereas secondary frequency reserve, FRR, is even dealt with 4-hour basis, even though for now it is only available in Austria and Germany. Well, we all agree this makes it challenging to ensure a decent business case with a multi-megawatt energy storage asset over a lifetime of 10, 20, or even more years. The market tends increasingly to short-term merchant business, whereas the early days of ESS saw essentially long-term contracts and often linked to PPA. Clean Horizon has found out that out of 177 operational ESS projects in Europe at the end of 2019, 76% were pure merchant projects. In the USA, on a similar number of projects, still 67% benefited from long-term contracts, but with a clear downward trend. What we also see is that early markets remunerating high power grid services tend to saturate quickly and therefore need to be substituted in most cases by more energy-oriented services. Well, luckily, as the market matures, new opportunities appear. New services are created, in particular linked to increasing penetration of variable renewables in our electricity system. ESS starts to compete successfully on capacity markets against gas peakers, and sector coupling and integration of e-mobility bear future potential for future value streams. EASE has published recently a comprehensive overview of existing, emerging, and future ESS applications. And I have just picked 3 examples here on the screen. Among the existing ones in green, we can find typically arbitrage in form of solar shifting, but also other services with an established remuneration mechanism. In orange, a couple of emerging services can be found, and in particular in the area of transmission and distribution grids. I here picked the example of reactive power compensation, for which we see first tentatives to define remuneration schemes in some countries. Finally, in blue, we have a couple of future, mainly ancillary services, in particular to enhance grid inertia in order to cope with the ever-increasing amount of synchronous generation. In many cases, we have a clear technical understanding, but not yet a suitable monetization or tendering framework for these services. These are just 3 examples out of this mapping of more than 40 services done by EASE. And the only purpose of showing you this table is to look at the different colors and to underpin that first, the variety of services across all front of the meter and behind the meter segments is quite amazing. And secondly, the fact that this landscape is permanently evolving, which means the industry needs to adapt. In the same time, the sector has to face changing technical conditions and market regulation. Some of you may remember PGM in the US changing their signal for frequency regulation services. Or another example, Ofgem in the UK introducing derating factors for what they call energy limited storage on capacity auctions. In both examples, the business case for energy storage was deeply impacted. On the regulation side, whereas the clean energy package, to take an example, in Europe, has laid the foundation for energy storage to compete on a level playing field in different energy capacity and services markets, there are also threats to the business case, for example, in the current debate on the FCR duration and other rules determined by grid codes. Well, in conclusion, we see that many future ESS will not operate to a single defined business model and operation pattern. They will need to stack multiple services, change services, or even add new services over the lifetime. Now, enough about theory. Let's look at a real case from a real customer. And I'm extremely honored to welcome Daniel Lacombe as the next speaker. Daniel works for Total Solar International, who is a developer of wind and solar power plants around the world, and more recently, also a developer and future operator of megawatt scale energy storage systems. So Daniel, the floor is yours.
Thank you, Michael. So what we decided to do in Dunkirk is to implement a project for a service to RTE being the French TSO. And that project was designed for a 25 megawatt hours capacity. And the design was focused on the FCR, primary reserve, as a core service. But we know that what we start with, which is FCR, may not live until the end of the 15 years time life of the project. And we know that we may have to switch to other services in the course of the 15 years. So what we did, we are Total Solar International, project owner, and so investor in the project. We have been implementing the project using 2 main contractors, Saft as a battery provider, and Omexom, which is a subsidiary of the Vinci Group, as an integrator and as the EPC contractor. And from Saft, designing the core equipment of the project, we expected to have a fit-for-purpose solution, A, and B, an economic solution, which would put us in a very competitive situation in the marketplace. And here is a short summary of the client specification that we passed on to the suppliers, Saft and Omexom. A, safety. Safety is a key concern, and we need to have very safe operations with the project. Then competitiveness, as I said before, is a must to make sure that we remain in the market. And competitiveness means we need a sustained capacity at the beginning of the life of the project, but until the end of the life of the project. So over 15 years, we need the reliability so that we keep a constant flow of revenues for the project. And that project was the first of its kind, but it was due to be repeated since we were awarded 130 megawatts by RTE in an auction when we got the result earlier this year. So this project is the first of its kind and is going to be followed by 4 other ones in the course of this year and the following year. So repeatability and the robustness of the solutions is quite important for us as well. And last, as said before, flexibility is a must, which means what the project is able to do at the beginning may change over time, and we need to adapt to new services that may take over part or all of the current FCR service which is envisaged. Back to Michael to explain what they did to serve us.
Well, thank you very much, Danielle. I would now like to share how we at Saft approach this need of flexibility, and then afterwards show you the solution we have effectively designed for Total in Dunkirk. I'll start by giving you an overview of the topics we will touch upon, the main points to consider and benefits to expect, and my colleagues Jim and Jan will then dive deeper into the different items. Well, based on, say, more than 200 batteries installed worldwide over the past 8 years, we have summarized our approach to flexibility around 3 main ideas. First, and quite obviously, make sure that the ESS is able to perform to multiple different operation patterns. In one word, it needs to be versatile. Secondly, enable an adjustment of the power to energy ratio over time. In particular, anticipate to increase the energy content for a given power rate at the point of connection. And third, think of keeping performance guarantees flexible so as to cover changing operation patterns. These recommendations may look self-explanatory and obvious. Still, the question is how to really make it happen. So looking a little bit more into the parameters that need to be looked at, you will understand that it is not enough just to judge a storage device by its nominal characteristics, which are the power and energy, its megawatt and megawatt hour capability. We need to look whether the power is available at beginning of life and end of life, what peak power can be provided, and how much power density can be supplied. We also need to look into thermal behavior and things like energy throughput. The benefits of doing this is to, first of all, avoid to redesign the solution for each single project. So you may benefit from a proven solution and learning curves from previous projects. Secondly, obviously, you may be able to adapt the operation pattern of your ESS when the market rules change. When it comes to augmentation, and when it comes to know whether augmentation does make sense, there are mainly 2 parameters to consider. First, is the operation profile stable over time? Will it work the same way over the next 10, 15 years, or is this operation profile likely to evolve? And then, depending on your application and business case, which is the KPI to be optimized? Is it LCOE, net present value, or upfront capex? Others. The advantages of anticipating future capacity increases are the following. You will be able to seize additional revenue streams. You will be able to augment when, but only when it is needed. And you may shift capex to OPEX and benefit from decreasing prices. Our last point deals with flexible guarantees. First, the question is, which performance parameters can be or shall be guaranteed? The most typical ones are uptime, remaining capacity over lifetime, and energy efficiency. But secondly, the question is how to measure and how to monitor these KPIs. Well, the benefits of a well-thought and well-implemented flexible guarantee are twofold. You secure the ESS ability to generate revenue, and thanks to a continuous monitoring of KPIs, you will enable early corrective measures in case there are any deviations. Well, with this overview, I will now leave the floor to my colleagues, Jim and Jan, who will illustrate more in detail the different technical, application, and business parameters that enable us to design a flexible solution, both in terms of product and services for our customers. Jim, the floor is yours.
Thanks, Michael, and hello, everyone. In this part of the presentation, I'm going to be talking about flexibility from the standpoint of applications engineering. And these are 5 key parameters that I'm going to be talking about in a little more depth. They're all interrelated, and the drivers here are the application that we're trying to address and the design of the system. So I'm going to start off by talking about aging. And for lithium-ion batteries, we can divide this between calendar aging and cycling aging. The two are separate and additive. Calendar aging is driven mainly by the thermodynamic stability of the materials in the cells. And it's dependent, obviously, on time. It's also dependent on temperature, and that's an exponential relationship. And for those technologies like NMC that have a sloping characteristic of voltage against state of charge, the state of charge is also linearly dependent on calendar aging. Over on the cycling aging, that's driven mainly by reaction kinetics. And the main dependency there is the number and depth of cycles, but also charge rate factors in here. When we charge a lithium-ion battery, we're driving lithium ions into the negative electrode. We're driving them through the passivation layer or solid electrolyte interface that's on the surface, and then they have to diffuse into the negative. And if we try and do that too quickly, we can cause premature aging. Energy throughput, I think, is very well illustrated by the change in the PJM regulation signal. When it was originally introduced back in the early 2010s, it was a fast-moving, fairly energy neutral signal that rarely went to the full power level. Now the latest signal is one that pegs at maximum power much more frequently, and there's a lot more energy bias there. So we're looking at much more throughput. And of course, then there's chemistry limits to consider, how many cycles we can perform per day, and also thermal limits. There we're looking at I²R heating, where obviously the current comes from the application requirements, and the resistance is driven by the aging of the battery through its life. So obviously, because it's I², the flexibility to address different applications is going to be limited more by the rate that's required than by the aging of the battery. That leads us into thermal management. So we've already talked about the operation profile of the application and the battery issues. Now we'll look at the design choices in a typical containerized system. There we're looking not just at the power and the efficiency of the HVAC, but we're also looking at the way the fans are operated and the ducting of the air, how efficient that is as it moves over the cells at removing heat from those cells. And the aims here are twofold. One is to limit the overall temperature rise in the container to the extent that that's possible. And also we need to minimize the variation between cells from the warmest to the coolest so that we have homogeneous aging. Energy efficiency, we've obviously touched on it here already, but we've seen a change in the market where previously people just looked at the losses in the power conversion system and in the battery itself to look at round-trip efficiency. And now owners are looking more globally at a higher level energy consumption that also factors in auxiliary power consumption. And there we've already talked about the HVAC operation. Fans have to be operated smartly. We can't just leave them on all the time to keep the temperature as even as possible. We have to operate them individually as hotspots arise. And we can address different applications sometimes by changing the set points of the HVAC system, but we always have to bear in mind the impact that will have on the auxiliary power consumption. The last of the parameters is the available power and energy. So we have a usable state of charge range, and that's going to be dependent on the rate at which we have to operate. And some applications require constant power as well as constant power in charge, I should say, as well as constant power in discharge. And that can mean that we're limited not just at the low end for sustaining a discharge, but maybe also being limited at the high end where we can no longer support constant power in charge. We can reach 100% state of charge, but that would be at reduced power if that's acceptable in the application. And that usable state of charge range is going to vary over the battery life. We also have to bear in mind that based on the design of the container, the power that's available to us may be limited by components other than the cells. So we're looking at things like cabling, connections, protective devices, and switches that may be limiting factors in the power. So all of this comes together with advanced modeling, and this is somewhat of a specialty for Saft. We've been developing and refining our modeling capability in MATLAB Simulink for something like 15 years now. And here we're looking at simulations of the electrical and thermal characteristics of complete containerized battery systems. So we can carry out this modeling at any phase of battery life, and that the results then feed into our aging analysis. And we can also quantify auxiliary power consumption. And to give a couple of examples here, the lower set of charts show cycling at 1 megawatt in charge and discharge, and the upper set of charts show cycling at 2 megawatts. In this case, the application profiles are artificial, basically to prove to demonstrate the points that we're making here. But certainly in my area, I'm seeing these needs constantly to look at different applications, different power profiles, not just with PJM, for example, in the States, but also seeing similar requirements in the Caribbean and in Latin America. And obviously, our application engineers are dealing with this around the world. So just looking at the center pair of charts in each set, the upper one shows the temperature profile for the cells and the ambient container temperature, and the lower chart shows the operation of the HVAC and fans. And obviously, you can see there that when we switch to 2 megawatts of operation, we're having to operate the thermal management system much more aggressively. And there's nothing special about that conclusion, but here we have the ability to quantify what that means in auxiliary power consumption. So that's my part of the presentation, and I'll hand off now to Jan.
Hello, everybody, and thanks for attending this webinar. Maximizing the value creation of an ESS before the actual operational phase is largely driven by the system optimal sizing, which itself is driven by 4 main drivers. First, the project required lifetime. Are you looking for a short-term 10 years merchant project, or are you looking for a long-term 20 years solar power purchase agreement? Secondly, what is the usage you are envisioning, meaning which kind of application and how those applications are potentially prioritized and stacked together so that you can maximize the energy throughput you get from your battery. Third, obviously, the CapEx investment figure. And last, the potential residual value of your battery at the end of a project lifetime, based upon the expected usage and engine profile, a value that you rather may prefer to minimize. One of the key parameters is your CapEx. Because of the continuous declining battery prices, because of the lithium-ion battery modular and flexible architecture by nature, because also of a potentially uncertain and evolving business model, it may be interesting to not deploy initially maximum capacity, but to delay over time some of your investments. So before we go further, let's be clear, there is no ideal solution. It's all about customer preferences and business case sensitivity regarding those 5 points. So let's talk about a real-life example, the case of a customer looking for adding an energy storage to an existing PV plant, mainly for time-shifting application, 1 cycle per day. But in that case, it was very probable that some additional application may be requested later on, especially some kind of frequency support or PV smoothing. Additionally, the PPA itself was not fixed at all, never its duration, never its price and escalation rate, nor the time-shifting power profile itself. So the high-level technical requirements we decided with the customer were pretty open, mainly a beginning of life capacity of 26 megawatt hours, a 10 megawatt nominal power, 365 equivalent cycles per year, a usual 97+% availability rate, and a lifetime at the project level of 15 years, but maybe 20 years. And this is where we supported our customer in his business case construction by showing future with 4 main different options and their specific advantages remaining by the pictograms. So option A, baseline, full usage. In that case, the batteries reach their end-of-life criteria after 15 years. Straight, simple. But you cannot go to 20 years lifetime duration, and you lack flexibility if your business case evolves. Option B, second baseline, in that case, limited usage, down to 250 cycles per year, allowing in that case to reach 20 years. But again, you lack flexibility if business is evolving over time. Option C now, it's the option A again, but with replacement, meaning that you just had new batteries to refurb the site at the end of year 15. The risk in that case is that you will have significant battery residual value at the end of a year 20, in that case more than 70%. And last, option D, an augmentation scenario, not the only one, but a specific one, supported by 3 augmentations over time. This scenario has been tailored for secure performance and maximal throughput, with full usage of a battery over 20 years, with always a minimal available capacity of 23 megawatt hours. If we look now at the numbers in details along capital expenditures, cumulative throughput over project lifetime, levelized cost of energy storage, and net present value, and if we use the baseline A as a reference, we obtain the following table. Note obviously that those results depend strongly on the PPA structure, assumed here in that case to be very competitive and stringent. As you can see, the option B, so limited usage, is not meaningful, leading to high LCOS and in fact a negative value creation. Option C, replacement, allows to meet project lifetime and use case. Limit upfront capex leads to positive NPV, but at the expense of higher overall capex, plus 50%. Also, NPV value creation in that case is in fact less than the reference, minus 30%, because of the battery large residual value at the end of the project lifetime. Plus, you also lack flexibility of usage. Last, the augmentation scenario offers, in that case, an equal LCOS, but the best value creation profile, plus 20%, thanks to better throughput and the smoothing of the additional capex over time. Additionally, the continuous larger capacity above 23 megawatt hours is offering you lots of flexibility for your additional application stacking, not even accounted for into the NPV creation. The limit of the 60% higher capex can be mitigated and financed thanks to a clear planning of the augmentation path and the cash generation of the project over the first years. Bottom line, the choice between full usage baseline or augmentation depends really on the risk assessment, the usage flexibility expectations, and the value creation. So there is no one-size-fits-all. Augmentation is not the only available option to cope with evolving business cases or with the need of flexibility to address application stacking and case complexity. The performance guarantees are an additional tool to tackle this need. Before going further, let's clarify a little bit the ambiguity that we met sometime between warranty and guarantees. Warranty covers defects or failure. It is not related to usage, but it's intrinsic to product quality, assuming obviously an adequate maintenance. Whereas guarantees ensure performances over time versus a usage profile, which obviously can be more or less constrained. Typical guarantees are capacity loss or aging over time, uptime, energy ramp-up efficiency, or even services themselves, such as mean time to intervene or max time to repair. So both warranty and guarantees protect your business model profitability, but only guarantees offer a toolset to address business uncertainty itself. Regarding performance guarantees, the key message is that there is a range of possible choice that does exist, allowing to arbitrate between guaranteed depth coverage and complexity. The simplest of all is the product guarantee. For an energy storage and with a high-level approach, it covers, for example, the parameters such as maximal daily throughput, cycling versus depth of discharge, state of charge window available, and so on. It has the advantage of being very simple, but most of the time, those values are guaranteed only for the nominal point of operation, and more, those values are fixed and static, whereas in fact, all those parameters are interlinked together. If you limit the state of charge window, you can get more cycling, and this kind of guarantee most of the time does not account for it. So let's simplify a little bit and represent this performance spider chart by a simple bubble. The next stage of performance guarantees are in fact at project level. So it's no longer a product push approach, but it's much more a customer pull approach. The first stage is guaranteed throughput. It's not very much tied to specific use. So again, it's very simple, but you do not capture so much additional coverage. The second stage is guaranteed performances. And in that case, it's related to more or less specific cycling. So it's a bit more constrained, but it offers a much larger coverage, and it offers some resilience versus the evolution of your business case over time. It's typically the kind of Saft usual guarantee proposal. Third and last, the guaranteed performances and rules. That's an even larger guarantee in terms of coverage, including rules clarifying the change of the guarantee parameters over time. But it has price and intrinsic complexity, requiring stringent data management and most of the time an advanced energy management system into the project to manage this guarantee. So bottom line, it's important to balance between business case complexity and coverage, so to pick the right guarantee. A good example is a PV time shifting project backed by a 20 years firm PPA that would clearly benefit and require a much less complex guarantee than a fully merchant grid services project. Whatever the guarantee, data are required, a lot of data. And not just data, but also automatic analytics, algorithms, and big data to crunch those inputs into meaningful and actionable results for Saft and for our customers. Saft remote monitoring and cloud Cube solution is a key enabler to support all kinds of performance guarantees. Cube is an integrated control command and monitoring solution at the same time, merging battery hardware, embedded software, and cloud software to ensure full continuity of data between operations, cloud storage, and data analysis. It allows to track battery performance over time and make advanced performance guarantees a reality. That being said, Michael, floor is yours again.
Thank you, Jim and Jan. We now come to the last part of our presentation, and I believe it is time to show you more in detail the technical solution we have designed for the Total Dunkirk project. As mentioned by Danielle, we have built a lithium-ion battery system of 25 megawatt hours with a 25 megawatt AC peak power to be installed on an industrial site in Dunkirk in France. This solution is built with 11 containers in TensioMax high energy, each providing 2.5 megawatt hours of storage capacity. These are connected to 3 groups of PCS and each with 3 or 4 low voltage, medium voltage transformers. So you can see here this basic arrangement of 3 or 4 containers, PCS and transformers will be the building block replicated on all future ESS systems Total will install in the frame of their contract with RTE. These will have different sizes and they may be bigger or smaller than the 25 megawatt hour Dunkirk system. We have simulated the operation of this system in multiple use case scenarios asked by Total. For example, 2 options of FCR services. One is with a full power at 200 millihertz frequency deviation and another one with 100 millihertz frequency deviation. The second one leading to much higher power density and energy throughput. These 2 could be, for example, options within the operation strategy of Total Flex, who is the aggregating flexibility entity and who has the goal to optimize the remuneration. And they may use one or the other operation pattern. We have modeled such different use cases in order to ensure first that the ESS is able to perform the required services over lifetime in terms of available power, energy, thermal behavior, and all the things Jim has explained to you earlier. And secondly, of course, is to assess that the aging behavior of the different scenarios are well known and understood, so to enable Total to optimize their operation strategy. Well, in the end, this assessment allows Total to use the ESS in a flexible manner and to optimize the operation strategy depending on the market situation at that very time, with now a clear understanding on the impact on the factors like aging, energy consumption, and so on. Furthermore, this solution is flexible because we can connect 3 or 4 or even more containers behind one single PCS. In fact, we have designed our standard container to allow flexible system architectures in terms of power to energy and system size. As such, we can connect a single container to a single PCS, that's obvious, but we can connect also up to 8 containers in parallel. And these 8 containers will be seen as a single storage unit by the PCS. Our proprietary control system called Cube enables this because it aggregates them all into one single battery entity. This control system is MESA compliant, so it easily integrates it to any higher level of EMS. It provides a local single HMI and it enables cloud communication. Furthermore, our solution is flexible with regards to voltage. We can have a 1000 volt or 1500 volt option. It is designed to withstand different difficult environments, whether it's high solar radiation or cold Arctic climates. And last not least, it bears a consistent safety concept that can be adapted to different local conditions. An additional word on safety, because this is of particular importance to Total on their petrochemical sites. Safety for Saft is not a matter of a silver bullet single solution. It's first of all a question of thorough risk analysis at the entire system level. So we need to capture electrical, electrochemical, thermal hazards and their combinations. We look at their effects and occurrence, and then we build different hardware and software safety barriers to detect, to eliminate, to mitigate, and to control these effects. And finally, once we have designed a single system, we extensively test components and the entire system to abuse conditions in order to validate the effectiveness of our solution, and in particular, of course, to get international certifications such as UL. Well, in summary, we have designed a single standard but flexible container. We can manufacture this IntensioMax high energy in 3 Saft factories locations worldwide. It's the same container wherever it is built. Assembly and testing is done in Saft specialized factory environments with Saft personnel. And this allows us to ship the product ready for plug and play to any place in the world, including remote or difficult areas. To conclude, we wanted to illustrate today that Saft is not just a developer and manufacturer of batteries. We integrate energy storage solutions with power conversion and power management components around the heart of the system, which is the battery. More importantly, we accompany customers during the inception phase, during the project phase, and after delivery and installation in order to design, implement, and service an ESS that remains flexible. We have in mind to secure our customers' revenues, making sure that the ESS we provide is able to operate reliably. We have in mind to secure your project, making sure it is thoroughly designed and implemented and operational on time. And we secure the service, making sure that the system is maintained and monitored in an optimized way. We do this by delivering ESS solutions designed around the battery, versatile, replicable, predictable, reliable, and future-proof. We do it by using extensively modeling to anticipate the performance of the battery over time, under changing operation patterns, and to assess the options of augmentation. And finally, we try to best balance risk and complexity on the one hand, as well as customer responsibility and suppliers' responsibility when it comes to guarantees. So this ends the presentation part of our webinar, but please stay online because we now come to a Q&A session, and therefore I hand it back to Andy. Andy, the floor is yours again. Thank you.
Thank you, Michael, and thank you very much to all the speakers. And yeah, thanks to everyone for staying online for the Q&A. Lots of questions came in, and as you can see, Saft did try and answer quite a few of those as we went, but we'll revisit a couple of those most popular questions and see what else comes in the next few minutes, I guess. Michael, first of all, should we just take a quick look at the poll while everyone else comes back on the stage? So we had the main challenges in making business with energy storage systems today. Nearly half of respondents actually said that the problems are financial. And I suppose it's quite nice in a way to think that, you know, people see technology as less of a barrier than they might have done in the past. But it looks like in close second place, almost joint second place, we have business and regulatory challenges. Michael, any thoughts on that? Different to what you expected?
Not really, and I think the fact that that finance is pointed out as a major hurdle is not new as such, but it also reflects right now the situation in the Corona crisis, of course, that would rather enhance even such financial issues. Now you may say, yes, we are happy to see that probably the market increasingly trusts integrators and suppliers on the technical side. But we also know that, of course, ESS is challenging when it comes to business because the business models are, as we said, evolving and not stable. So we try to be at the side of our customers to reinvent or to adapt and to find the best solution pretty much on a case-by-case basis because it's evolving.
So it's flexibility in all areas, really, I guess, and you know, not just in the raw technology itself, I suppose. Okay, so very quickly before we do get into the Q&A, I can see people have already started responding to the second poll, and that's up on your screens now. Which topics would you be interested in for future webinars? And yeah, we can already see the answers are coming in quickly. You can choose between ESS control systems, safety deep dive, energy storage systems on islands, microgrids and energy storage, a deep dive into augmentation, and sustainable batteries. And I think you can reply to, I think, more than one answer on that. I think it's possibly 2 might be a maximum, but that gives you some options. So we'll take a very quick look at that again before we close the session for today, shall we, Michael?
Thank you.
Yeah, excellent. All right, so going through some of the questions that came in, and lots of questions, obviously. And let's kind of start this chronologically. So obviously there's going to be some things that are a little bit commercially sensitive that I think, you aren't necessarily going to answer directly, but clearly you're happy to speak with people, take those offline possibly. There was a question earlier on that that you guys flagged up as an interesting one. Which country is in the forefront for energy storage supplies? And I guess you could kind of broaden that question really to mean, which are the markets, I guess, regionally that are exciting at the moment.
Yes,
do you want to open that one up, Michael? Yeah.
Yes, we were hesitating answering this directly because it depends whether you look at it from the supply side or really from the market side. On the market side, I mean, clearly the US has been a major driver for energy storage systems for many reasons. I won't go into details right now, and it will remain the market for energy storage systems in the coming decade. Australia, of course, as well is an important market, and we expect China, who has taken a major rank now, to increase. Of course, because China also is a big country as such. So these are probably the leading ESS markets. Now on the supply side, well, it's not a secret for what concerns lithium-ion batteries, and lithium-ion represents the majority of energy storage systems. We have had major suppliers from Korea for what concerns the cell manufacturing. By now, we see a number of Chinese suppliers, and of course, there's also a well-known reference in the US. Now, this being said, the cells, the electrochemical part of it is not all of the supply side. Of course, it's about integrating energy storage systems, and there we see a broad variety of players, let's say, on the international scene.
Excellent. And just like to revisit a question that had 8 participants voted it up from Hannes Laggett. And it's about considering the stacking of services from energy storage systems. So I think, the question specifically is at the same time, simultaneously or consecutively, what are typical combinations of revenue stacking that are feasible? But do you think perhaps, Daniel, do you think you could maybe answer briefly on the types of stackings of revenues you're targeting with Dunkirk and possibly with future projects?
Yes, indeed. In Dunkirk, we're going to stack 3 services. The core one is going to be the FCR, also called primary reserve, which is the one which is of interest for the TSO, the French TSO RTE. And together with it, we will stack a capacity mechanism, which is going to add some revenues. That was designed by the French TSO to encourage the investment. So these 2 for sure are meant to be stacked. And then we'll do a bit of training just to manage the set to charge of the battery. That will be an additional service and revenue, but second order to the others. But then, more generally speaking, you don't stack services. You may play with them during the day, depending on the value of the various streams you may get from the services. So the arbitration used to be made in the past for long-term services with selling your capacity weekly, for instance, for the primary reserve. And now it became daily, and it's going to be for a few hours, which means you're going to jump from a service to another one, but not stack. You're going to do intraday arbitration more.
Right. Okay. And so there's a question just below that on the type of warranty that was offered. Now, I don't suppose you can tell us specifically about, you know, that project and kind of the relationship between Saft and Total on that. But Jan, maybe you'd like to just talk us through perhaps some of the, the ways that you would consider the sort of energy throughput metrics that Total would be dealing with in a project such as Dunkirk, and kind of talk us through, you know, how you'd arrive at the best solution for a customer in that respect, I guess.
Yeah, with pleasure. So basically, in that case, if we are talking about throughput, it's clearly a question of performance guarantee. In this kind of project, which are grid services with pretty complex use case and application, all the idea is to have, let's say, the mileage, cumulative throughput, calculated and guaranteed in such a way that at least the minimum business case is ensured for quite a long time, but also at the same time to give some flexibility, especially if the frequency control rules from the TSO are changing over time, so that the mileage minimum guaranteed is still the same, whatever the change. One example is if the services is moving from 100 millihertz symmetrical to 200 millihertz unsymmetrical, the minimum mileage guaranteed at the beginning of the project needs to be ensured so that the business case is still flying at the end. And it's typically the kind of potential option we can evaluate with our customer. And it has obviously an impact both on the initial sizing to cope with this kind of uncertainty, but also on the performance guarantee contractualization.
Okay, so I mean, designing warranties is kind of, it's a fairly complex situation, and I guess picking the right one that can work over time is pretty much essential, I guess, and something that you're, I presume, quite happy to have an extensive dialogue with to figure out, I guess. So there's a question here that I was quite interested in terms of cybersecurity. Michael, I'm not sure if you want to maybe take this one from a general perspective, or if either of the other guys would like to chip in. But yeah, Oliver Forsyth says this may be most relevant for battery energy storage in the US, well, not necessarily just the US, but how is cybersecurity considered by Saft when designing the system? And actually, if we could open it up a little bit to just basically ask about communications protocols in general, because I see there's quite a few questions about that, and I don't know if it's hitting more than one bird with the same stone, but if you could maybe just talk a little bit about that sort of communications protocol between energy storage systems, the grid, and the operators, I guess.
Yes, the first thing that inspires me is that if there is such an interest on this, we should probably organize a webinar with our developing engineers and specialists on this. I must admit, I'm not really I do not have the in-depth answers on this, but maybe in a couple of words. First of all, yes, we redeveloped our entire control and communication architecture. We made it compliant to the MESA standard, which is pretty much US based. However, for us, this could become a general protocol and a standard for, say, grid-tied energy storage systems, and standardize the way we interact with superior levels of communication and controls. Mm-hmm. Concerning cybersecurity, well, we developed and certified our system against the international cybersecurity standards, and I must admit I don't have the name of the standard or the number of the standard in my mind, mm-hmm. But we will answer in detail on this if you are interested in a later stage.
Excellent. And actually, there is an email address that we should probably give out, isn't there, Michael, for people who would, not just on cybersecurity, but in general. And you'll give this out at the end again.
For those who want to note it right now, yep. Please, if you have specific questions or if you want to contact us, you can send us a mail to contact.webinar@saftbatteries.com. But there will also be a direct a link at the end of this webinar, so you can directly contact us through a connection at the end of the webinar.
Sure. Michael, I guess it's a bit of a generic question. Well, I don't know if I guess it's an important question, but there's quite a few, and there's always discussion broadly speaking, between NMC and LFP when it comes to talking about energy storage. But there's a couple of questions here on what type of lithium-ion battery you're using. Which do you see as Nick Kitchen, who's with Cumulus Energy Storage, I believe, says, which lithium-ion battery chemistry do you see as optimal from cost, safety, and performance perspective for solar PV and storage applications? And I think maybe if Daniel could answer that one as well, that would be interesting, if Daniel has got an opinion there.
Maybe I can comment first on this from a global Saft point of view. Well, Saft is a developer and manufacturer of batteries, and among the technologies we have lithium-ion technologies, but we do have several. We develop and manufacture several lithium-ion technologies, whether it be historically NCA, now NMC, and but also LFP, and we use them in, you may know, very different industrial markets, ESS being one of them, but we are also in space and defense markets, other stationary markets, mobility, and so on. Right now, we use NMC for ESS because for us it's what we consider the best technical performance and cost for, in particular, partial state of charge operation. Now, this is the status today. Obviously, we have ongoing developments in technology directions, short-term, medium-term, long-term, in system solutions. But this will probably reveal in future webinars or in other contacts to you. Right now, NMC for us is the best solution for ESS and the type of applications we are looking at.
Right. Sure. Okay. Now, is this a fair question here? I think you've got one from Florence May. What is the largest capacity lithium-ion battery Saft has used as a case study? And how's the cost efficiency at higher capacities compared to other forms of energy storage? Thermal, pumped hydro, compressed air energy storage. Is that something we really want to be talking about today, or?
The system sizes we are working on right now is in the area of several tens of megawatt and megawatt hours. And you know that lithium-ion as a dominating technology for energy storage goes up to 100 or 200 megawatt. If we are talking about compressed air or pumped hydro, it's the order of magnitude above this. These are really what we would call long-term bulk energy storage solutions, and they are used for different purposes. Difficult to compare them on a dollar per kilowatt hour basis, in particular because you would use a lithium-ion ESS on a daily basis, or even on a you would maybe charge and discharge. We talked about throughput, the battery, several times a day, which is not the case with other storage solutions. So difficult to make a general statement unless you compare for a given application the LCOS, so the leverage cost of storage on a per kilowatt hour basis of these different systems.
Certainly, yeah. Should we just take a quick look at the second poll and see how those answers are coming in?
Sure.
Yeah, and looks to me like ESS control systems are just taking a lead with 29% of respondents, and microgrids just after that with 28% of respondents. That said, we have 21% would like to look at sustainability in batteries, and 10% apiece or thereabouts on augmentation deep dive and ESS on islands. And safety deep dive is maybe a bit surprisingly, it's just at 3% there. What do you think, guys? Any comments?
We both of us lost our bet because it's not what we expected. But that's the beauty about polls. So it's really interesting, and we'll for sure take this up and try to provide further information and webinars, in particular around the control system. And also microgrids is probably something we would be very keen to talk about. So I would maybe at this point I'd like to thank the audience for responding to this, for the interest, and for most of them staying with us over and beyond our 1 hour of webinar. We have seen a lot of questions. For this also, thank you very much. We were not able to respond to all of this in 45 minutes. We tried to do our best to respond afterwards to the extent possible. And from my side, thank you very much to all the speakers, and I hand it back to you, Andy.
Okie dokie. Do you think we should maybe just do 1 or 2 more quick questions before we call time?
Sure.
Yeah. Okay. Well, I'll try and wrap up a few of them into one into one question, if at all possible. So I think a lot of people are asking about basically components and supply chains. There was a question on, where you geographically assemble your systems. So I think rather than trying to respond to all of them, there's one about inverters and power conversion systems. There's one about battery cells. Do you just maybe like to, and I know you did briefly go over this during the presentation, but yeah, just essentially give us a quick overview on your kind of strategies for either developing in-house or for procuring those main components of the systems, really, I guess.
Yes, sure. For what concerns the battery cells as such, I mentioned we either produce them ourselves for, let's say, more high power oriented systems. And for the Intensity Max high energy we presented here, we have a supply agreement with a Chinese supplier. For what concerns the power conversion systems, we work with a limited number of power conversion partners. So we are able to integrate depending on the geographical location of our customers, the application case, and different technical requirements. We are able to integrate most of the well-known PCS components into our systems, and we often work in a consortium mode, for example. And we add to this the power management system. We typically do not, at least we do not have in our own developments an energy management system. Our strategy is to integrate with very often customer-based energy management systems, in particular when we talk about customers on the utility side.
Thank you very much, Michael. And of course, thank you very much to all of the other speakers. So yeah, I think that was a really nice way of looking at a lot of different aspects of systems, system designs and control strategies. So before we get on to the questions, shall we have a quick look at the poll that we launched at the beginning of the session there? Yeah, the answers have come in and the people have spoken. What are the main challenges in making business with energy storage systems today? And in fact, nearly 50% of people said that the main challenges are financial. I think that kind of tallies with what happened in the earlier session that we held today for some other markets. Around 22% of people said regulatory issues. About 16% said technical, 13% said business, and nobody found any environmental impediments to making business with energy storage systems. So, Michael, and the guys, any surprises with that, do you think, from the poll?
Well, I think it's not a surprise as such, but the fact that financial issues were leading here also reflects the current situation with the coronavirus, which I think enhances financial problems. On the other hand, we see that it's a little bit spread over the other segments as well. So it confirms that doing business with ESS is challenging with regards to different aspects. maybe not so much environmental items, which could be more pronounced in Europe, for example, than in the USA.
Certainly, seeing the one thing I've noticed is that regulatory has jumped a little bit from the earlier session, I think, hasn't it, as well? So I guess kind of changing regulations, and it's always a question that the technology moves a bit faster than regulations, I suppose, is another way of looking at it. Okay, well, let's just quickly, so people do keep your questions coming in, so we've got a few more minutes to take new questions. But actually also, can we just launch that second poll? Sorry, can we get the poll back up on the screen there? Well, if not, it's on the right-hand side of your screen. So I can see people have already started answering. Which topics would you be interested in for future webinars? Sorry about that, thanks. Yeah, so you can choose from ESS control systems, a safety deep dive, energy storage systems on islands, microgrids, subtly different there, augmentation deep dive, and sustainable batteries. So yeah, we'll take a brief look at that before we wrap up for today. So thank you very much for that, and yeah, we can go back to video. And so in terms of the questions, we had lots of questions rattling in. Should we ignore the first one that I covered in my intro, because that 50% to 80% figure was actually for if your electric vehicle is idle for many weeks on end. So apologies for that. I should have made that clearer. Now, one question that I found really exciting was the question about the destination and environment that energy storage systems will be put in, and the different design considerations you have to go through. Now, I've written about a lot of projects by a lot of companies, I guess, but Saft, I remember I spoke with you, Jim, about maybe 4 or 5 years ago about a project in somewhere in Alaska. And I know you guys have done projects in very different environments as well. So is that something you can maybe just talk to us a little bit about, you know, what some of those different considerations are, and perhaps some of the challenges, and what's really exciting about that, I guess?
Yeah, sure. When we're talking about energy storage systems in the far north, the environment is difficult, the transportation is difficult when we're dealing with ice roads and ports that freeze over and so on. So that's been quite an important part of our business over the years. And for the Arctic systems, we use high-tech insulation so that we're minimizing the amount of heating that we have to do, because obviously we need to keep the batteries in a good operating environment so we get the maximum value from them. We also use hydronic heating coils, so we in many cases we can take advantage of hot glycol solution from a diesel plant, and we can use that for heating the energy storage container. So it's about taking a holistic approach. The other aspect of operating in difficult environments is in island systems. There we have to deal with often a lot of condensation, saline environments with the corrosive aspects, and there it's about smart operation of the thermal management system, so that we're trying to keep the battery not too far below the dew point if we're going to be working on it, and obviously having corrosion resistant components.
Right, okay. And I mean, there's plenty of other stuff we can probably go into on that, but I guess you know, anyone who's interested to learn more on any of these topics that we don't quite get to get through, you can contact Saft later on, and we'll give you a number for doing that. So another question that was very highly voted, and I guess we could have predicted that this would come up, is the kind of dynamic between lithium iron phosphate and nickel, manganese, cobalt, and indeed, you know, the various flavors of lithium, if you will. So I don't know if, Michael, you want to maybe give an initial bit on that, or if
yeah, sure.
Yeah.
Of of course, it's a broad subject. We cannot deal in detail here. In a nutshell, both technologies, say iron phosphate on the one hand and nickel-based lithium-ion systems such as NMC or NCA, have their respective advantages and drawbacks, and it cannot be summarized by just one is better than the other. At Saft, we develop and build different lithium-ion technologies, both nickel-based and iron phosphate, and we use them in the various typically industrial fields of energies of storage, whether stationary in the UPS field or in military, marine, and so on. And we use the technology that is most suitable or provides the best performance and safety for a given utilization. For ESS in particular, the current system is an NMC because for us, for in particular partial state of charge operation, that is a very suitable solution. But of course, we do not exclude using iron phosphate today or in the future on other application and market segments. The particular point about iron phosphate is what Jim has mentioned earlier. In terms of application, it's the lack of slope, which makes the management of iron phosphate in state of charge quite challenging.
Right, sure. And the questions are rattling in really quickly here. So I don't know how we what sort of attempt we can make to answer as many of them as possible. But obviously, you guys will be answering some of the questions in writing as we go. There's a question that's just come in that maybe could be elaborated on. Maybe one for Jan here from Gabriel Estevez. Is it possible to achieve 89% efficiency in the system? I'm not sure why exactly that number, after 10 years in operation without replacing the lithium-ion batteries. But if you can maybe use that, Jan, as a bit of a launch pad to talk about how to kind of maintain, high efficiency in systems over a long period of time, I guess.
Maintaining very high energy efficiency depends on many topics. First one, obviously, is the AG chemistry aging itself. I mean, the internal resistance of your battery. And this is mainly driven by the physical law and chemical laws, and on that, nobody can anything, but also the quality of a product itself. So here, it's really quality by design. The second thing is how you manage your auxiliary power consumption, especially the HVAC and this kind of stuff. So basically, at the end of the day, by good design and good product quality, you can maintain over the long run a pretty good energy efficiency. Now it's also depending on the use case. The more you are using the battery, the older it will get and faster. So there is no absolutely, let's say, absolute low, but in any way, maintaining 99% for 10 years seems to be very challenging. Even though if you have a very easy use case, that's not easy. Right,
sure. And very quick follow-up question on that. Steve Druitt has asked, what are the technical challenges of capacity augmentation, i.e. mixing batteries of different age behind the same PCS? Do older batteries compromise the performance of newer batteries or vice versa?
Okay. So here, first of all, augmentation has many challenges. Challenges front on the AC side, because you need control algorithm to manage your whole fleet of batteries of different ages. But there is effectively also challenges behind the PCS. One of them is that effectively you are mixing batteries of different ages, so different capacity, different power rating, and different, let's say, internal resistance. So to manage that, clearly you need good control algorithm. And you need also to be able to align batteries which are, let's say, properly sized so that the overall state of health is compatible. you can mix different ages, but you cannot mix absolutely everything. So you need to have a very good understanding about your chemistry and the history of the previous batteries and what you can really put in terms of new batteries. There is some limits. Mixing chemistries themselves, meaning LFP and NMC, for example, behind the same PCS is not a viable solution. So you still have limit at the end of the day. And
Sure.
If I could just add to that, this is where NMC does have an advantage, that sloping characteristic of voltage against state of charge means that when you put battery strings together in parallel, they will just share the current according to their relative internal resistance, and because they're in parallel, they have to be at the same voltage. And with that sloping characteristic, they're also at the same state of charge. So management of parallel strings of different ages becomes much easier. There's not a lot of extra intervention you have to do.
Right, sure, okay. So pretty comprehensive answers there, guys. Thank you. The question has had a couple of recommendations this is one on safety, I guess, and it's from Travis Liana, who says, do the containers have fire mitigation or fire detection? And more broadly speaking, I guess, what is the trend moving forwards in the utility scale market? Who wants to take that one? Michael, do you want to have a start on that?
Yep, I can first of all answer definitely that we do have fire detection, well, smoke detection, fire detection and mitigation measures, which are detection of smoke and a fire suppression system in order to avoid any major incident. Now, safety protection devices are around fire and thermal runways, but they also include and must include, for example, management of gases and pressure inside the container. So we have additional devices. Safety in the container is not only just a fire suppression system. It deals with, as I tried to explain shortly, the different electrical, electrochemical, and other hazards that can appear. I have a little difficulty to answer to what is the trend in the US. I think after the incidents, there is quite a big awareness about the complexity of the safety issue, that there is not a silver bullet. And I think that many manufacturers or integrators do look into the issue and adapt thoroughly their solutions to this, and of course including fire suppression systems, water spray systems, and others. So the industry matures and finds more sophisticated and reliable solutions to this challenge. Anything to add, Jim, on your side?
No, I think that's a good response.
Thanks.
Sure, okay, thanks for that. And yeah, there's a question literally just come in from someone called Ben Kerr, who is, I think it's a pretty appropriate question for the US market, but also actually possibly from a solar perspective. So Daniel, since you've managed to rush back to your house and get back online to be with us, I don't know if you maybe would be able to talk a little bit about the question, Daniel, where it says, in the applications referenced, does Saft see more AC coupled or DC coupled systems? And how does the team foresee this changing moving forwards? So it's the difference in working with AC and DC coupled systems.
Well, I can talk about our experience, which has been AC coupling, and we do network service, so it's high voltage AC. Mm-hmm. And I could not comment on DC coupling because for our utility size systems, it's AC, basically what we do. Yeah. And DC is probably for smaller systems, but maybe my Saft colleagues will answer on this one.
Oh, apologies.
Yeah, I could add a couple of comments there. AC coupled systems are generally more flexible, more capable in terms of the ability to add other solutions, other services to a system. When you have a DC coupled system, it's generally, not always, but generally behind a unidirectional PV inverter, as opposed to having a bidirectional converter on the AC side. DC coupled systems have the benefit of somewhat improved efficiency because you don't have to go through transforming to medium voltage twice to get the storage, to get into the storage. And also DC coupled systems can be a little easier to get permitted because the authorities having jurisdiction don't like to see more inverter capacity than the facility is rated for. So if you have a 50 megawatt PV facility, you don't want to go adding a 10 megawatt AC coupled inverter system, because then they're thinking you'll go over the limit of the interconnection. So when you're DC coupled, that's no longer a possibility. So there's pros and cons to both.
Okay, brilliant. So terrific answer there. So sorry for putting you on the spot there, Daniel, and thank you nonetheless for joining us anyway. So I guess just time maybe for one or two more quick questions, I guess. And there's one that's had a few upvotes here from Calixta Dufresne. Could you elaborate on how you guarantee uptime from the design, redundancy level, if any, down to maintenance strategy? So it's guaranteeing uptime of the system, I guess. And I'd better ask who'd like to take this one.
So it's a very, very good question. Uptime is a very large, complex topic in the sense that there are many, many factors impacting this uptime performance. Let's say first family is all the product design, reliability, modularity, and so on. Second topic, there is the project architecture and sizing itself. Is there any oversizing? How the system is branched? Is it multiple single lineup in parallel, or is it some very large lineups? All that affects uptime very clearly. And then you have two other buckets, much more operational. The first one is how do you share your maintenance between Saft and the customer? How you bring capabilities to react very fast on the field with some local people, will it be from customer or some local partners, that affect a lot the uptime. And the fourth and last bucket, and how you design your maintenance plan and your capability to support remotely into maintenance. So all the remote diagnostic, advanced troubleshooting, be able to restart a system remotely, and all these kind of aspects that at the end of the day provide, let's say, this uptime performance. Now, one very much key point is between the uptime performance and the uptime guarantee, there is also another point, which is if the performance is, let's say, low, but in appearance, but that the penalties for not being up are not very high, there is no reason to really push towards a project which is always up. I will give you an example. Let's say counterexample. If you are connected to the grid with a grid services capability in terms of rated power on a yearly basis, you need to be up all the time. For example, frequency support of many kinds. Now, if it's a solar project and you just do solar time shifting, being done at night for planned maintenance, for example, is not a trouble. So again, this balance between performance uptime and performance guarantee needs to be tied and analyzed versus the application and versus, let's say, the business risk or the penalties for this business case. So it's a balance.
Terrific. Okay. I think we're probably going to be running out of time, kind of more or less, well, now really, I suppose. But should we take a quick look at the second poll before we start saying goodbye to everybody? And so topics would people be interested in for future webinars? It appears that ESS control systems is in the lead with about 36%, and then joint second, although there's a bit of a race between augmentation, deep dive, and sustainable batteries, with microgrids shortly behind that, and ESS on islands and safety deep dive kind of somewhere in the back there. So any surprises in that for you guys?
Well, it means we still have a lot of things to do, and people are equally interested in different subjects. So it's a positive feedback. Of course, the ESS control systems is a surprise to us, and so we both lost our bets this morning. But we're happy to see that that there is interest in the other subjects, and we will definitely use this experience to address them in future webinars.
Yeah.
Maybe a word from my side. We are definitely overwhelmed with all the questions. We try to answer as good as possible. We still remain a little bit online, but clearly, first of all, we will respond individually to all the questions by mail, which we may not have been able to answer today.
Yep.
You can also click here and ask to be contacted, or otherwise you can send us a mail to the following address: contact.webinar@saftbatteries.com. contact.webinar@saftbatteries.com. In case you have additional questions, you want to get in contact with us, you want us to contact you, and we will be pleased to follow up then on this webinar.
Brilliant. Yeah, no, it's been absolutely excellent fun. And as Michael said, the web address is contact.webinar@saftbatteries.com. And yeah, of course, they will be trying to answer the questions. If some of you stick around in the right-hand tab, some of the questions will get answered by the experts here. So yeah, I'd just like to conclude by saying thank you very much to everyone who attended. A good couple of hundred people in there, and yeah, some really great questions. Some nice comments as well from some of you. So yeah, from our side, thank you very much from everyone at Solar Media and Energy Storage News. And over to you, Michael, if you just want to say goodbye to everyone there, I guess.
Well, first of all, thanks to you, Andy, for moderating this webinar, or the two sessions today. It's quite late for you by now.
No problem.
Thanks to my co-speakers, and of course, a big thank you to the audience staying quite a long time with us online. Thanks for your questions, and I hope this is an ongoing dialogue we have with this audience. This being said, thanks again very much. Have a good day or evening, and bye-bye.
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 Goodbye, everybody.